Right, so how does the concentration of the reactant affect the rate of reaction? Well, we define it in terms of a rate law. Now notice the emphasis on that word law there. Law means experimentally derived, okay? Rate laws don't try to explain anything. Rate laws just say what is going on, what happens, okay? Now rate law is always of the form rate equals K times the concentration of reactant 1 raised to the power, in this case of X, times concentration of reactant 2 raised to the power of something, in this case Y, times concentration of reactant 3 raised to the power of something, Z, etc., etc., etc. Right? Anytime you've got a rate law, it's got to start rate equals K and then times the concentration of reactants, each raised to a particular power. Okay? K is called the rate constant. It is a poopy constant. It's a horrible constant. It's pretty much a pointless constant because it's only constant for a given reaction at a particular temperature. Right? Breathe in the general direction of the reaction, you'll raise the temperature, and thus the rate constant changes. When you do this in a lab, then when you're examining the kinetics of a reaction, you gotta keep it at a constant temperature, because as soon as the temperature changes, that constant is no more. The only time that you're doing it at different temperatures is when you actually want to look at the effect of temperature on the rate constant. Okay, rate constant, about the worst constant you're going to encounter in your life. And the trouble is that it is, of course, extremely important in chapter on the chemical kinetics, on rates of reaction, i.e. this chapter, but then as you'll see, we're going to use constants that effectively come from the rate constants for just about the rest of the course. So the poopiness of this constant is actually a far-reaching poopiness. Now then, these powers are called the orders of reaction. You can have the order of reaction in each reactant, you can have the overall order of reaction, which is of course just the sum of the orders with respect to each reactant. So this reaction is X order in the first reactant, Y order in the second reactant, Z or Z order in the third reactant, and X plus Y plus Z order overall. Okay. The nice thing about the order of reaction is they depend on the reaction. Okay, they do not depend on the temperature under normal conditions. You've got to do something really weird in order to get the order of a reaction changed. Okay, so that means that when we talk about how does the concentration affect the rate, we focus on the orders of the reaction to describe the reaction rather than include K. We only include K when we want to get really specific about a specific temperature. Okay, indeed, we only determine K when we've got some weird, nefarious reason for doing so. Let's look at a few examples associated with this rate law, because by the end of this slide you need to have, or the end of this show I should say, you need to have a really good grasp on exactly what a rate law is. Well, first of all, consider this reaction. Very unrealistic one, 4C plus 32D goes to poop. Now, the reason why I say goes to poop is because we don't really care about the products. Okay, the products at the stage of conversation we're having have got nothing to do with the rate of the reaction. What we're interested in, we're starting off and then we're doing the reaction, right? That process of the reaction. Where we end up is of secondary importance, and so thus using poop in here is designed to demonstrate, to add emphasis to that. What's important here, how do the concentration of the reactants affect the rate? Okay, let's say I tell you that this reaction, we've determined that it is third order in C and fifth order overall. By what factor would the rate of the reaction change if the concentration of C were quadrupled and that of D were halved? Okay, well, what I've just told you is I've told you effectively the rate law. Rate equals K. Every rate law starts with rate equals K times the concentration of C cubed, because I told you it was third order, times concentration of D. Now the order of D has to be 2, because I told you C was third order, fifth order overall. This 5 is 3 plus the D. Thus the rate law is rate equals K times the concentration of C cubed times the concentration of D squared. Notice it's got nothing to do with the coefficients. Okay, that's going to be something really important in this chapter. You can't just look at the coefficients of an equation and say the order, right? Unfortunately, when we get to our next chapter, that will all change. But right now, coefficients, exponents, nothing to do with each other. So anyway, let's continue with this particular question, right? We're taking concentration of C and we're quadrupling it. We're multiplying it by 4. Well, what does that do to the rate? Well, the rate has to do with the concentration of C cubed. So if we multiply C by 4, we're going to multiply by 4 cubed, which means that the rate is going to go up 64-fold. All right, 4 cubed, which is 64. Now we also are taking the concentration of D and halving it. Well, how does the rate depend on D? The rate depends on D squared. So the rate is going to change by that half squared, okay, which is a fourth. So the effect of quadrupling C increases the rate by a factor of 64th. However, halving D, right, multiplies it by a factor of a quarter, all right, decreases it by 4 if you want to use fancy words. And so therefore what happens to the rate is that it gets increased by 64 on the one hand, but multiplied by a factor of a fourth on the other. So the rate overall increases by a factor of 16. Okay, so that's an example of how you utilize the rate law once you got it. How do you get it? Well, consider a different reaction. 2A plus B goes to more poop. If I double the concentration of A, then the rate doubles. If I triple the concentration of B, the rate increases by a factor of 9. Determine the rate law. Well, this is the same thought process but flipped. Rate is K times A to the power of X times B to the power of Y. Okay, nice general rate law associated with the reaction between A and B. Got it? What we got to do is figure out X, we got to figure out Y. Well, let's start off here with the concentration of A part, the bit in green. If I double the concentration of A, then the rate doubles. Well, whatever I do to A, I do to the power of X. So I doubled A, so the rate is affected by doubled to the power of X. Well, in this case, it's just doubled. So what must X be? X is 1. Now we've sorted out the A part, let's have a look at the B part. Okay, if I triple the concentration of B, then the rate increases by a factor of 9. Well, whatever I do to B, the rate happens to be to the power of Y. So I tripled B, so that means that the rate is going to be affected by tripling to the power of Y, and I'm told that it increases by a factor of 9. Well, what must Y be that when you triple B, you get an overall times 9? Y is equal to 2. So therefore, rate law is rate equals K multiplied by the concentration of A to the power of 1 times the concentration of B squared. Again, to emphasize it, it's first order in A, second order in B, third order overall, and notice that the orders of the reactants do not come from the coefficients of the balanced equation. We'll see times when that's true, but you can't ever rely on it. Okay? Let's make a little bit more complicated one, shall we? How would we actually go into the lab and do this? So let's consider this reaction. We'll do a real one now, right? 2NO2 plus 2H2 goes to N2O2 plus 2H2O. Now the first thing I want you to do is I want you to convince yourself this is balanced. This is one of those funky little equations that a lot of people get extremely distracted by in terms of the balancing process. And now what we're going to do is we want to get the rate law, and let's, for fun, get the value of K at the particular experiment, right, using the following data. Well, let's look at how we would get this data. First of all, we'll say rate law is rate is K. We want to figure out K times concentration of NO2, that's one reactant, to the power of X. We've got to figure out X, times the concentration of H2 to the power of Y. H2 is the second reactant. We want to get Y. Absolutely no reason at this stage why X should be 2 and Y should be 2. Those just happen to be the boring old coefficients of reaction. Nothing necessarily to do with the order of the reaction. Okay? So we'll set up a pretty little table, and we're going to do some experiments in which we look at different concentrations initially of the NO2, first reactant, different initial concentrations of H2, the second reactant, and we're going to determine the rate. And the way we'll determine the rate is, of course, we will plot out the concentration against time of one of our reactants, or maybe one of our products, depending on what we can actually measure. We'll plot the little curve, so it will either be going down or be going up. We get the slope of the curve, right, at time is 0. If that slope is the initial slope of a reactant, good, we're set, that's the rate. If the slope is the slope of a product, then we're going to have to turn that to a reactant using the stoichiometry and the relative rate argument to get the rate. So first experiment, right? Let's go, and we find we got some 0.25 molar NO2, we got some 0.25 molar H2. Mix them together, plot out that little graph, take the slope, and we find the rate is 2. Notice I'm giving you nice numbers because I'm nice. Well, now we're going to do a second experiment. What would we do for the second experiment? We're going to change concentrations and see what the rate is, right? See what effect changing the concentration has on the rate. But would we change both of these? And the answer is no. When you're trying to see what's going on between two different things, you only change one at a time. So what we'll do for our second experiment is let's keep our NO2 constant, but let's use a different H2. So now we can see what effect changing H2 has on the rate. And we find in our play experiment that the rate is 4. Well, how does this help us? Well, from experiment 1 to 2, we doubled the concentration of H2. And what we found is that it doubled the rate. Well, what we expect changing H2 to do is to change the rate. Changing H2 to the power of y would change the rate. So in other words, this is times 2 to the y. We doubled the H2, so doubling to the power of y should be the effect on the rate. Well, we doubled the rate, so therefore y equals 1. Okay, so we know what y is. Now let's go ahead and do another experiment to help us figure out what x is. Well, what would we do in this third experiment? If we were an Aggie, we'd take totally weird numbers. As we're not, what we'll do is we'll change the NO2, excuse me, to 0.5, but we will use the same number for H2. We could have used 0.25, we could have used 0.5 for this, as long as we had one of the ones we've done before, so that all we're doing in experiment 3 is we're changing the NO2. Well, going from experiment 2 to 3, what did we do? We kept H2 the same, and we doubled the NO2. What effect did this have on the rate? That was the effect it had on the rate. So now let's go ahead and investigate. We doubled the concentration of NO2, and when we did that, we found that the rate went up by a factor of 4. Well, of course, whatever we do to NO2, that to the power of x would be the effect on the rate. So therefore, this 4 is the doubling to the power of x. So what must x be? X is 2. So therefore, we can say right now, the rate is K times concentration of NO2 squared times concentration of H2 to the power of 1. And ordinarily, that would be it. We determine the rate law. But this one here, it said, I want K as well. Well, how do we do that? Here we are. We know the rate law, and here are our data that we obtained. And notice that in experiment 1, we do the rate. We know the rate. We know the concentration of NO2, we know the concentration of H2. So all we got to do is plug them in. We know rate, we know NO2, we know H2, plug it in, we get K. Plug it in, 2 equals K times 0.25 squared times 0.25 to the 1. K equals 128. And that, in theory, is all you actually need to do. But you have a wonderful opportunity here to double check yourself. It's not often you get to double check yourself in this course, but this is one where we do, because it shouldn't matter which experiment we took to get the value of K. It should be the same value of K for each experiment, as long as we were careful experimentally and kept the temperature constant. And so while they should be the same, that means that if you work out the K for all of them, or at least enough ones where you can be sure that you've changed every possibility and K's are the same, you know you're right. If on the other hand K is different from one experiment to another, you've messed something up. So let's actually do that for both experiments too. Right, 4 is K times 0.25, blah, blah, blah. K is 128, feeling good about ourselves. And also for experiment 3, plug in everything in. K is 128. Thus, overall, we can say rate is the 128, that's the value of K, times NO2 squared, times H2 to the power of 1. Now, that's the process. However, if I was to leave you there, then when you saw someone's on the book or on practice exams or the homework, let alone on the exam itself, you would be possibly floundering. So I'm going to finish this slide now because we've been going for over 15 minutes, and then the next PowerPoint will be completely one question. Okay, and it's going to look just the same as this one, determine the rate law, except it will be a little bit meaner.